I know that. And feel free to read the 50 years. Oh, you did? Oh, you did it online? No, I wasn't. Thank you very much.
Good evening, everybody. Was that too loud? Is that better? Okay, sorry about that.
No, that's good.
Thank you all so much for coming tonight. My name is Jordan McGee. I am Director of Education here at the museum, and on behalf of our entire staff and board, I want to welcome you all and thank you all so much for coming this evening. Tonight's lecture is a special one because it is part of a global event called Asteroid Day, which takes place annually on June 30th. There are events like this one and some different ones happening all across the world. Of course, in some places, June 30th has already come and gone. But for us here in the United States, events like this are taking place all over the country. We are the only event in Nevada, and this is our third year doing it, and we're very proud of that here at the museum as one of Southern Nevada's premier STEM institutions, and we thank you all for coming to participate with us. So the point of Asteroid Day is to bring awareness to the hazards asteroids can pose to the planet. And June 30th was chosen because it is the anniversary of the largest impact in recent history, the Tunguska event in Siberia in 1908. So it's been a while, but we have asteroids coming near the planet all the time, and our speaker tonight is going to talk a little bit more about that. It is my pleasure to introduce our speaker tonight, Ben McGee, who, yes, also happens to be my husband. But before there are any accusations of nepotism, I want to tell you that his events at the museum this year, he's doing another lecture in November, were booked before I came into this position. However, I would invite him to speak here any chance we had to have him, because not only is he a brilliant scientist, he has the unique ability to explain scientific concepts in a way that make all of us feel as brilliant as he is, at least while he's talking about them. So we are very lucky to have him here tonight. He is a multidisciplinary scientist with experience in hydrology, geology, and geophysics, space science, and radiation health physics. However, you may have also seen him in your very own living rooms because he has been a host and subject matter expert on a variety of television programs for Nat Geo Channel, the History Channel, Weather Channel, Travel Channel, a whole bunch of them. So he may be familiar to you from one of those shows. And he's currently a senior scientist for NS Tech and Mercury on the Nevada test site. It is my great pleasure to introduce you all to Ben McGee.
Thank you very much. I set the bar pretty high there. I'll try to live up to it. And so, yes, first I want to say thank you to Michael Hall, the museum director, and the National Atomic Testing Museum for having me and for doing this 3 years in a row. And I think it's important and particularly relevant for Nevada. There's some strong connective tissue here, which if any of you have been in my earlier ones, you'll see. But I'm trying not to tread over old territory here. So today, the talk's entitled Nuking Asteroids. This is briefly, this is what the talk's going to look like, the requisite talk about what I'm going to talk about slide. So I'll try and navigate this, and if you guys have any questions while I'm talking, actually, go ahead and pipe up, it's okay. And there'll be a Q&A afterwards also. A little bit about my background. Jordan already went over it a little, but I've got a geology degree from the University of Wyoming, and I've been a space geek my whole life. So I was watching volcanoes erupt on one of Jupiter's moons back then. I'm almost finished my master's in space studies. I took a break and decided to get my boots dirty for a while. So that's what I was doing in betwixt, working on asteroids, how radiation affects them in space. I've worked at the Southern Nevada Water Authority out here. I worked as a radiation shielding specialist and a crew systems manager at Bigelow Aerospace, also here in town for a while. This is actually a picture of the beam spacecraft that we've got on board the International Space Station right now. It's the inflatable spaceships, if you've heard about that. But that doesn't mean they're going to pop any more than your tire or your car would pop. You kick it, it'll break your foot. And then, yes, I did sort of stumble onto TV work. There's a smattering of things that proves that, yes, that's true. It's a happy accident, and that's a story for a different time. But I got very interested. I also teach part-time at the community college when I can, and I got very interested in trying to promote science concepts to people who are interested in them. I think there's a lot of people who are underserved. You know, I don't believe that there's any such thing as a silly question. So yeah, I currently work at the Nevada test site, and that kicks us into Asteroid Day. So again, like was mentioned briefly, what is it? Technically, they say it's a global awareness movement where people come together to learn about asteroids. And really, it's pushing on what we can and should be doing about them. Now, the first part of this, I don't expect you to just believe me that we should be doing something about them. I'm going to show you. And a lot of people have come on board to support Asteroid Day, and it's actually gaining momentum. So it started in 2015, and they've got some celebrity scientists aboard, but it's now International Asteroid Day. In December 2016, it just happened, the UN, the Office for Outer Space Affairs, just formalized Asteroid Day as a global event. So this is a way of bringing everybody to the table, because asteroids don't preferentially fall in one hemisphere. I mean, this is a threat that, if you believe it's real, it affects us all. And really, for me, what do I think Asteroid Day is? It's summed up perfectly by an old Larry Niven quote. Sometimes it's attributed to Arthur C. Clarke, but he said, hey, the dinosaurs became extinct because they didn't have a space program. If we don't have a space, if we go extinct because we don't have a space program too, it'll serve us right. So basically, the dinosaurs weren't aware of the hazard, so how could you blame them? But now that we know that this stuff can happen, well, yeah, shame on us. So again, why June 30th? Mentioned briefly, it was the Tunguska blast. Now, it was a while before, it was actually the latter half of the 20th century before we really started finding evidence that asteroids hit us regularly. And why? Because they were masked. In Tunguska, there's no crater. And I'll mention why, but it's estimated to have been about 10 to 15 megaton equivalent explosion, but it blew up midair, probably because it was a comet or a very loosely consolidated asteroid, more like a rubble pile. So like a shotgun blast, it hit the atmosphere and just came apart and blew up. But the blast wave still hit the ground, and it knocked down about, estimates at 80 million trees. There are only a few surveys from the beginning of the 20th century that went over there, but it was like nothing we've ever seen before. You know, with only a few pictures, and this is pictures of an equivalent blast mushroom cloud. So, and by the way, mushroom cloud is not unique to a nuclear explosion. Mushroom cloud happens anywhere there's any heat. So that's why giant thunderstorms can make a mushroom cloud, they call it an angle cloud. You know, so it's just heat rising. That's the nature of the mushroom. So if you have any large explosion, it'll look exactly like a nuclear one. So what are asteroids, right? Why are they out there? Where do they come from? They're leftovers from the early solar system. You can think of them as samples. And they're samples specifically, in most cases, of parts of a world, an old world that was fractured. And there's a really broad size range, and you can see here they go all the way down. You got teeny tiny ones. This thing's about 300 some odd miles across. For Vesta is a popular target for people who are interested in asteroid names. And Ceres is actually, it used to, like Pluto, but we didn't know about it. Most of us now don't know about this. Back in the 19th century, Ceres was a real planet, bona fide with its own symbol, and it was on all the maps. And it's sitting right, it's the lord of the asteroid belt, we know now. So it's big enough to have become round. And now, today, when astronomers found all the asteroids back in the early 20th century, they demoted Ceres. Okay, well, it's just one amongst many, and so therefore it's not a real planet. And with the new definition, the same thing happened to Pluto. That when they discovered that Pluto is now one object amongst many, they downgraded it. But what they did is they made a middle zone. So they upgraded Ceres from asteroid to dwarf planet, and they downgraded Pluto from planet to dwarf planet. And now, at least it's consistent. But geologists are arguing they should all be planets if they're around. That's a different story. So what does it mean? Why are they around? Well, here's one of the most interesting things about the asteroid belt. And I didn't know this until I started doing graduate work in it, that there are chemical fingerprints in the asteroids, which are unique. We can tell that certain asteroids are related, and more importantly, meteorites that fall here, we can tell which asteroids they came from in some cases, which is pretty exciting. The fingerprints are that unique. But what we found is that there are enough unique fingerprints represented in the meteorites that fell here. That means that there were 80 worlds, at least, that aren't the ones that are on our solar system maps, that have long since perished, and all that's left are these little bits of junk left over that hit the Earth and fall, and we may find them from time to time as a meteorite. And so this word differentiated just means when something gets big enough, there's enough weight forcing everything that's in the center that it melts. And then you get the light stuff floats to the outside, and the heavy stuff sinks to the middle, and that's differentiation. That's how you make a round world. That's how you go from a sort of potato-shaped asteroid to something that looks like a planet, like Ceres, as you cross this threshold. And so what you got is 3 basic parts to any planet. You got a crust, which is the light stuff. You got the mantle, which is the middle, and you got the core in the center. Well, that pattern becomes important because that means that there are just 4 types of asteroids, and therefore 4 basic types of meteorites. Now, people who are professionals in asteroids and meteoritics would take issue with me, but this is basically all there is, and it's devil in the details stuff. Now, why? Well, you get parts of the crust. Ignore the terminology if it's confusing. Yeah, technically achondrites. But you got like basalts, like volcanic rock. What our crust is made out of, what any planet's crust is made out of. Okay, well that's one kind of asteroid. Imagine that a world blows up or is fractured apart. Well, some of the pieces are going to come from the crust. Well, then you also get stony iron called pallasites. Well, that's just a piece of the mantle from an ancient world. And then you go all the way to the core. These are iron asteroids or iron meteorites, which are the most common. These are called Wittgenstein patterns. So this is particularly interesting to me that you'll see this in antiquity. The metal that fell from the sky was very precious, and it's stronger than all bronze alloys. So it would act like magic metal back then. If you etch the surface, you see these telltale patterns. What these are 2 nickel-iron alloys growing together. And you may say, gee, man, this is all terribly interesting, but why are you telling me this? Well, it's because we can't make this happen on Earth. The reason is to make 2 minerals called camosite and tanite. Forget the terminology, it was confusing. Sorry about the jargon. I tried geologists for doing this. Anyway, 2 nickel iron alloys. If we try and get these to grow together, they just won't do it. The only way is if we cool them down on something like 1 degree per million years. It's the only way to get these minerals to grow together. And so about the only place that you can do that is a world that's slowly cooling off over time, just like our moon. So eventually all planets will lose their core heat, and it will go from molten and slowly crystallize. So if you get one of these cool meteorites and you get it sliced open and you see it etched, this is actually something only nature can do. And this is an era where, we pride ourselves on being able to do mostly anything, but we just don't have the time to do this. And so, and again, also there's something cosmic about it. You're holding the heart, a piece of the heart of an ancient world. And mostly not one of the ones certainly not one of the ones that's out there today as a world that we have on our solar system maps. So a new way to think about the metal asteroids, where did they come from? And certainly the meteorites, what are you holding? And then there are these things that are really interesting to scientists. They're undifferentiated, they're called chondrites. Basically, if you get just a lump of stuff that never got big enough to melt, these are original droplets from the cloud from which our solar system formed way back. And you can see that it's little spheres like raindrops, but in space. Like, why are raindrops round? Because they're in free fall. They're in 0 G. Well, same thing why astronauts take water out of their pouch, it floats around in little spheres. That's why everything in a chondrite is a big conglomerate of little spheres. So anyway, these are samples of the early solar system, is the way scientists think about it. So that's it. You get the crust, the mantle, the core, and some original stuff. And that's all there is. Those are the types of asteroids out there. So that's what they are. It's a shotgun blast of asteroid geology. Now, where are they? For the most part, they're in what we call the asteroid belt. They're kind of shepherded in the solar system by the huge planets, like Jupiter mostly. And between the orbits of Mars and Jupiter, or trailing in front of or behind Jupiter, kind of lumped into groups. And even though there are lots of asteroids out there, this number surprises people. In total, it's only about 5% of the mass of our moon. So if we started out with 80 whole differentiated worlds out there of varying sizes, we have no way of knowing how big they originally were, but you'd expect that there would have originally been a lot more material out here. So this shows that the solar system's been fairly well cleaned out. Okay, that's a mark in the, well, we shouldn't sweat getting hit by something. It shouldn't keep you up at night, right? And for people who are interested in mining this stuff, there are 3,600 billion kilograms of material out there, and if any of it's precious, you start doing the math, and it gets very exciting. But here are the ones we're really interested in. That's what we call the main belt, is what I showed you before. But here are near-Earth asteroids. What that means is asteroids with orbits, and you see this cloud is made of little loops. Well, near-Earth asteroids cross at some point in their paths around the sun. They cross our orbit. So that's like traffic drifting around in a lane. That means that these guys are moving through our lane. Now, the timing has to be just right to hit us, but this is where, when we talk about something like asteroid day, we're not worried about main belt objects. They're out there, they're happy, they're fine, they're not coming here, they're very far away. It's these guys that we occasionally get close to. So, I updated my 2016 talk. Why worry? So what, this, I don't expect anybody to hit the I believe button. Well, why worry? Because lots of material routinely hits us all the time. And you see them as shooting stars. And if you go over, I think it's a 16th of an inch or so, that's where you create enough friction when they hit to light up in the atmosphere and burn up and sprinkle some dust on the planet. Current estimates say there's about 100 tons of small meteors or meteoritic dust that falls into the planet per day. Well, that's about 7 Volkswagen Beetles raining down from space per hour. So, it's a cartoon, but think of it, that's across the whole planet, but you can think about that as real material. So yes, the Earth is slowly getting heavier, if you want to worry about the force of gravity or something. Not really, it's spread out over the whole planet. But that's the small stuff. It's pretty at night, but not threatening unless you're those one in a gajillion stories. I think there's one woman documented who was ever hit by a meteorite and it struck her side or so. So it makes lightning bolts strikes in commonplace. So ordinarily, not have to worry about this. Well, what about the big old stuff? That's where the geology comes in, prehistoric stuff. Well, what put this on everyone's radar back in the 90s? We found a crater off the Yucatan Peninsula, long buried. It doesn't do this, it doesn't make a crater shape on the surface of the ocean, which is why we couldn't find it. It's since been eroded and covered with other stuff, but we realized that you could measure things like the density of the rock, the strength of gravity in the rock, and other things that teased this pattern. And this is the thing, as we found, researching the globe, they took out the dinosaurs. And there's some arguments about whether this was combined with volcanism or not, but it's definitely happened at the same time the dinosaurs went out. So, and it blew out enough material to spread a layer across the world that we could find. And there's certain remember I said you can find asteroids by a fingerprint? Well, hey, it left that fingerprint in that little layer of geology right when the dinosaurs went out. And that's when geologists started going, wait a minute, we find this stuff in meteorites. We find that, looks like we find it in asteroids. I think we got hit by an asteroid. And it's surprising I think it's surprising to a lot of people, and it was to me now, that this is so very recent. I mean, it wasn't until the end of the 20th that people really started taking impact seriously. But there it is. And there is a handy rule of thumb, in case anyone wants it, that if you see a crater, the thing that made it is roughly 25 times smaller. The math works out pretty well. I mean, it's a generalization, or if you know the size of the asteroid, it'll create a crater 25 times larger than it is. And now that's not the overall impact, the blast wave and the heat and getting buried by stuff, that extends much farther than the crater. But if you want to know how big the actual final hole will be, you just multiply the asteroid by 25 or divide the crater by 25 to get a beat on what hit it. And then this is what I was talking about. This is the actual geophysics that started to reveal this circular shape and multi-ring structure. You only find this. It's very similar to the moon stuff for a good reason. Okay, well, that's the famous one. Then we started tracking out other stuff. Chesapeake Bay. People, I don't think many know, Chesapeake Bay, yes, is an impact crater site. It's about 50 miles wide. So the one that took out the dinosaurs is about 100 miles wide. Chesapeake Bay is about 50 miles wide, an inner and outer ring in the crater. And again, the geophysics is what really brought it out. There's no crater shape over there now, it's all been buried. But as the technology got better, we started finding it. And even here, if anyone was here for my talk last year, there is now confirmed as big now as the one that took out the dinosaurs, but far older, 370 million years ago. That information was really buried, and it only peeks through the ground in a few spots, which is why it was so hard to find. But I've climbed up there with my own eyeballs, and here you can't even really use the geophysics in the same way. Things like seismographs and electromagnetism and stuff. But you find the shattered rock, and that stuff is only made in a few ways. And when you look at details inside the shattered layer, well, there are fingerprints that show this wasn't an earthquake. This was getting smacked by something really hard. So there you go. We call that an impact breccia, shattered rock. And then we get to about 50,000 years ago. Come forward to almost historic time. Meteor crater in Arizona. This one's a very popular feature now. Come and drive up. I like mentioning that we couldn't prove that this was an asteroid crater until after a famous geologist, a planetary moon guy, geologist named Gene Shoemaker, saw this. He thought it was an asteroid impact. He was all by himself. All the rest of the geologists at the time said, it's cryptovolcanism, strange volcano. Okay, all right. Well, he had an idea, but it wasn't until there was a shot called Teapot S out on the Nevada test site that made a crater that Gene noticed was identical in certain key ways to this crater. And we know that new crater on the test site excavated something. So he realized that an explosion underground shooting stuff out is exactly the same as something coming in and exploding underground and shooting stuff out. And after seeing that nuke, he came back and was able to prove this was an asteroid impact. So it's backwards, I think, from the way people, it's so obvious, I think, to many people. No, it looks like, we've got great pictures of the moon and other planets, it looks like an impact crater. But the test site was the key to unlock the meteor crater was an asteroid, which I think is pretty cool. Okay, well that's all old stuff. So far, I don't think I should have convinced any skeptics that we really need to be worrying. Like, okay, 65 million years, 370 million years, even 50,000 years ago. I mean, if I were going to make betting odds on that, I think nobody would come to the table. So, why worry? Well, what about big new stuff? And you say, well, Ben, wouldn't I have heard if there were any big new stuff? Well, we did. I think about 100 years ago, there was a 15 megatonner that went off, and for scale, that's 1,000 times stronger-ish than the ones that were lit off over Hiroshima and Nagasaki. 1,000 times stronger. 1,000 of them. That's big. It's equivalent to the biggest bomb the United States ever tested, Castle Bravo, which is the picture on the left. So that is the equivalent sized nuclear explosion, the cloud rising way up into the stratosphere, the really terrifying stuff. Okay, fine, well that's one. Didn't hit the ground, do I really need to worry? Well, then we start bringing in modern astronomy. In 1994, there was a comet in Shoemaker-Levy 9 after the same Gene Shoemaker who decoded the meteor crater thing, trained Apollo astronauts too, and so he was in the thick of all that. 23 years ago, 1994, this comet, it got too close to Jupiter. Jupiter ripped it apart, and then slowly, all of the pieces, one at a time, bang, bang. And we knew it was going to happen because the astronomy was good, so everyone turned their telescopes in. What you're looking at here is an infrared picture of Jupiter. So there's the great red spot over there, I think. Oh, maybe it's too low. Anyway, might be another scar. Anyway, we watched a bunch of these fragments go bang, bang, bang. This is a picture of one fragment. I think it's a G fragment. The explosion from one of them was larger than the Earth. This is the Earth to scale on Jupiter. So Jupiter, in this case, took one for the team.
Ben, how large is Jupiter compared to the Earth?
The ratio. Well, you look, you can see. I mean, the Earth is this big, and Jupiter is this. I can pull that number for you afterwards if you'd like. There was a volume mentioned. No, I'm going to screw the numbers up. Jupiter is enormous. I mean, you're talking thousand Earths. It's got to be more than that. Anyway, you're talking orders of magnitude larger than the Earth. So its gravity is stronger also, and that's why Jupiter is able to shepherd all the asteroids around and pull them into itself for the most part. This is like the big brother that protects you on the playground. Jupiter has been doing this presumably for a very long time, and we finally saw it happen. But now we've got evidence of older big impacts, but suddenly we watched an explosion go off. It would have just obliterated the Earth with our own eyes. And for the people who are into this sort of thing, that kind of makes the hair on the back of your neck stand up, like, whoa, okay. And so that one made the history books, and that's when a lot of researchers started saying, we need to think about asteroids. We need to do something about asteroids. We need to have a plan. Let's figure out how to stop an asteroid. And everyone went, yeah, okay, fine, and whatever. Then 8 years ago, it happened again to Jupiter, and we missed it. But we saw the same impact scar, this black cloud. And this is the Earth to scale now, and you're really zoomed in on Jupiter. So the scar is about the size of the Pacific Ocean, the whole thing. So now all of a sudden, that's an explosion about the size of Earth-ish, once a decade, happening on Jupiter. Okay, now maybe it's getting worse. And then again, the asteroid guys are like, hey, let's get a plan together. We're seeing this stuff happening. And it goes, well, that's interesting, but that's on Jupiter. Okay. 8 years ago. Now, Chelyabinsk, 2013. This is an event that happened over a town called Chelyabinsk in Russia. And what you're seeing are 4 still images from different dash cams that happened to catch the event. An asteroid came in to our atmosphere at a low angle, thankfully, sort of like a skipping stone. Blew up, was 40 times brighter than the sun when it did, and trailed away into the distance and ended up leaving a few big chunks of itself in a lake, and left a huge lateral mushroom cloud, if you want to think of it that way. And then you could actually, well, I think there's a better picture next. Oh, and I have a video, if you'll indulge me for a second. Yeah, and there have been several good YouTube videos that have come out since people have uploaded things, but now there have been a few years since it was here. They're really good stuff. So I sequenced some of this stuff together. So let me blow this up here. Now, I want to point out a couple key features too. Here's what we call the bolide. So the flaming asteroid as it comes in through the atmosphere, and it shows up. This is real time. This is not computer graphics. It hasn't been doctored. This is what it would look like. And it explodes, and it comes in very fast. You're talking, I think, 12 to 20 kilometers per second. I'll show you what happens. Comes in, he's totally silent, blows up. That's during the daytime. And then you see bits of it trailing.
Where was that?
in Chelyabinsk, Russia. Now, I want to point something out to you too, that everyone saw it was 40 times brighter than the sun. If you're indoors, it would get our attention in here right now if something 40 times brighter than the sun happened out there. Because all of a sudden, this shine would come in through the doorway because of all those windows out there, and we'd all go, huh? I mean, it would be noticeable. And so then we'd all kind of be inspired to go, hey, what was that? Well, you guys know that when a lightning strike happens, unlike the movies, you see the flash, and then you count, and then the sound hits. Question?
How many miles an hour was that?
I think I got the number converted on a future slide. I'll get that for you. But it's whatever, the intercept velocities are about 20 kilometers. I'll get you the miles per hour. It's not on the slide. Really fast, like 66,000 miles an hour, something like that. Yeah. So, but like a lightning bolt, you don't hear it, you see it first, and then the sound wave travels, right? Well, the same way, this thing blew up with such intensity, we now know it was half a megaton. There's a huge shockwave coming. It's following the sound. But it's invisible. So when you see a huge flash like this, it's just enough time at 15 miles, if the speed of sound is 667 miles an hour, at 15 miles, how long does it take? Well, just long enough for everyone who's not thinking about that to go, what's that? And then go outside and see this amazing cloud, contrail. So now it's after sunset. This thing is still lit up because it's so high in the sky. It's 15 miles up, so it's very obvious. Everyone's crowding around to look. And right about when they think, hey, can I get a better look at that? And the blast wave hits. That's the sound of every window in a town breaking at the same time. And then every car alarm going off at the same time. So, this is 15 miles away, and it did that much damage. So anyway, I just thought that was a break up a static PowerPoint a little bit. So,
Was there any chance they were worried they were being attacked?
yeah, I think, well, it's alien enough. I mean, if it had come straight in and hit the ground, I think it would have been a very different scenario, and we would have been close to an international incident. But because it came in sideways, it was just weird. People hadn't seen it before. So I think some of the stats here are coming. Yes, so to do that kind of damage from 15 miles away, 60-foot diameter, it injured 1,500 people in that town. It damaged, when all was said and done, more than 7,000 buildings. The explosion was silent. Like you saw, plenty of time to watch it go by, leave this contrail, say, call your friends, man, get outside, look at this thing, what is it? It took about 71 seconds if you were right underneath it, and longer if you were at an angle. Now maybe a minute and a half, 2 minutes. You're just going, wow, what a beautiful cloud. And then all of a sudden, it gets very serious. Yes?
For people that don't know, the Soviet Union had 2 nuclear laboratories that designed nuclear weapons, and Chelyabinsk was one of them.
Really? Oh, that.
Yes.
This for everyone that didn't hear it, Chelyabinsk is the site of one of USSR's nuclear laboratories. Bit of irony there. So yes, thank you for pointing that out. And so it was the equivalent of about 50 Hiroshima bombs. And if since you're in here, you might be into this sort of thing. The point of explosion, see where it went brightest. These are from dash cams that are farthest away. That's, you can think of the friction going up until you literally heated that thing up until it failed. And then it sprayed into the air and then everything lit up and then there was so much thermal release that it exploded with the force of a nuke. There is actually a mushroom cloud coming up from the contrail at the point of explosion. And you can see some pretty cool, if you track it down on YouTube and things like that, pretty cool video of it. So yes, in the video, I jumped the gun. So now we're out of things that make astronomers and geologists excited, right? This is something that happened in real time, injured a lot of people, and it was a wake-up call, and it was a global wake-up call. And it's no surprise that 2 years later, Asteroid Day organization is founded by several other research institutions and nonprofit organizations.
Throw in, it was the same exact day as the beer mass.
Yes. That's a good point. By just dumb luck, there was I think a 45-foot diameter asteroid that also passed through the keyhole between us and the moon right at the same time. So there was a lot of attention tuned in, and yeah, that's a good point.
Is it so fast that we can't see it? Like, a scientist can't see it ahead of time?
Yeah, well, it depends. That's an excellent question. If it's out there, sure, we can see it. I mean, think of the Earth is moving at colossal speed around the sun. So is Mars. So is the moon moving around us. So just because it's moving fast doesn't mean that it's too fast to be detected by a telescope. But the problem is if it gets too close, it's crossing more angles in the sky faster. If you're not looking at the right, you have a limited amount of time to see it. And certainly, if something comes straight in, say something is moving at 20 kilometers per second, well, there's about 20 kilometers of thick air between us and space. So if it comes straight down, that means 1/1000. And it's gone all the way through the atmosphere and hit. So in a lot of movies, they do it wrong. You see it in the distance, and it's approaching, and it's like, what are we going to do about it? No, at the point that you see it, that's why the dash cam is so useful. It's glowing, and that was coming long ways. It's glowing, and then it's in, and then it explodes, and that's the most time you have if it's right here. But, so say that you could argue, Ben, that's an isolated incident, probably not going to happen again. And yes, sir.
Did anyone see this in advance, or this
Nope.
catch everyone question?
Nope, this one was a surprise. We had no idea. And because it was small. We've been focusing small as they go. We've been focusing, as I'll mention later, on big stuff that could really screw up the whole planet. But if you are still not convinced that we should worry about it, I submit to you Exhibit A. The moon. Right next to us. And we've been spending a lot of time getting excited about the impact craters that we found on the Earth in recent times. All you got, it's smaller than us. It has weaker gravity. Its net is weaker and closer in. We have a stronger net, if you want to think of it that way, to grab asteroids. So they'll be coming faster when they come in, and we'll get more of them than the moon does. So just by pure logic alone, there's no way the moon has psychically known where all the asteroids were coming and positioned itself to shield the Earth. So if it has this many, what's different about the moon than the Earth? Well, we've got erosion, we've got an atmosphere, we have active geological processes that are currently resetting the slate. But zoom in. There are so many asteroid impacts on the moon that without tracking down a scale, I cannot tell you how far away I'm looking right now. Because every one of these is a crater, all the way down to the little dots. That's how many. And so, we learned from the moon there's statistics. We know based on how frequently big ones hit the moon to small ones, you can see it here, more small ones than big ones, you can start to develop curves. When are you most likely to get hit by something? So the astronomy guys have been saying this for a while now, but it's only until the Chelyabinsk blast that I think this started to resonate with people. Maybe it's on YouTube, therefore now it's real. So, nukes in space, nuking asteroids. And this is an in-joke to my very first Asteroid Day talk, where I said, you might expect coming to a talk like this me to talk about some harebrained scheme to try and blow up an asteroid with a nuke. And at that talk, I said, nope, there's a different relationship I'm talking about this time. Yes, that's exactly what we're going to talk about here. We're going to talk about, can we actually use weapons of mass destruction as planetary defense? All right. Well, let's evaluate it. What did the movie, and that was Bruce Willis from the movie Armageddon, which I call it the Armageddon scenario now. What did that movie propose? Because I think that's where the idea of an asteroid, trying to do something about an asteroid impact, people were introduced to it most frequently via that movie. Well, they say in the movie, there's an asteroid the size of Texas, and it's coming in 2.5 weeks. For anyone who knows anything about mission planning, or how long it takes to build a rocket, or just get any organization at all to sign anything, 2.5 weeks is not enough time to do any, just to like put your name on the plaque on the door for head person to deflect asteroids. So anyway, they get everything together and they've got to try and they ferry some nukes up to this giant asteroid, and Bruce Willis spoiler alert, Bruce Willis sacrifices himself to save the Earth. Okay, well, if you're going to actually poke on this idea, you can start to ask the question, okay, well, have we ever blown up a nuke in space? The answer is yes. And we did a few. There's Project Argus, it had some smaller ones, but the one I'm going to focus on is called Starfish Prime. 1.43 megatons. This is a real decent sized nuke. It was atop the old Thor rocket. We blew it up at 250 miles above the surface of the Earth, well into space. The international boundary for space, it's a smooth transition, but you cross 62 miles up, you get your astronaut wings. 250 miles, you're clearly in space. Oh, that's for the International Space Station orbit. So, anyway, oh wait, it's at 250 kilometers. Miles. Oh, anyway, you're up there. So what happened? It blew it up, it created brilliant aurora. And this is where people don't realize, again, generally, the aurora borealis, for the North Pole. What is that? That's the Earth's magnetic field trapping radiation from the sun. We branded it solar wind, but really, it's radiation. What is the sun? It's a giant gravity-driven thermonuclear fusion reactor wailing away at the sky with such intensity that at 93 million miles away, it's warm. We walk outside and look at the beautiful, I used to joke that a sunset's only beautiful because it's really, really far away. What happened? Well, we created, so that's radiation trapped by the Earth's magnetic field slamming into the Earth's air so hard that it lights up like the fluorescent bulb. And that's the aurora. So there, when you see a picture of aurora, you're actually looking up. You know, those lines aren't lateral. You're like looking up a really tall skyscraper into space, watching this stuff coming in at you. So, surprisingly, we created our own aurora with this blast. And this is 11 o'clock p.m., July 9th, 1962. So this is at night, Johnston Island. And this blast lit up the sky like the sun for a moment. Well, this is what we've all seen pictures, I think, now of what conventional land-based fireballs look like. But what do they look like when they're in zero G? Well, they're spherical, and they end up with a ring structure where they intercept the light particles of atmosphere that are way up there, because technically there's still some things to interact with. And I think, yes, I think this is the point where this didn't work in better, but it'll work here. I just want to show you guys what this blast looks like, because I think it's kind of amazing. So it's just going to loop. But you can see this squiggly dark line in front is actually the rocket contrail. You're looking up, and the wind is blowing it around, so you're looking way, 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 way up, and then it blows up. You see, it's a concentric sphere, but there's all this math revealing itself in the boundaries. Yes. Oh, question. I'm sorry.
Did you say that was launched from the Johnson Island?
Yes. Yeah.
Oh, okay.
Correct me if I'm wrong. Yeah, I'm pretty sure that yes. And I just think it's because then you see the material collect back in the center and then rebound back out. So there's all this really interesting physics that's going on, which I would love to know more about, but there's only so much data on it. But anyway, to answer the question, have we blown up any nukes in space? Well, yes, we have. And so let's keep poking on the idea. Full screen. All right. So in Honolulu, 900 miles away, there's the flash seen through clouds. And they saw the artificial aurora all the way down to New Zealand. So we stopped doing tests like this in part because the effects were very dramatic. This is also, these aurora lasted 50 minutes. It looked like this. There's a cool Air Force picture from the sky that one of the guys on board took of the aurora. So presumably, point of detonation was here, and it's starting to be distributed through the upper atmosphere. So and we actually created a fair bit of additional radiation, sort of a fake, a real, but man-made radiation belt, like the Van Allen belts. A lot of electrons we threw up there, devil in the details. But we stopped doing it because it was taking out our own satellites. Telestar, stuff like that. So what sent it up there? The old Thor rocket. It was suborbital, so you won't really get to an asteroid on it, but it proved that large nukes in space will work. They're heavy, you can get those guys up there. And with modern rockets, the intercept problem's not an issue. We can get it going fast enough to get to an asteroid. They're near Earth anyway, so it's all about timing. All right, let's keep going. Is it kaboom enough? That's really the question. I mean, are our nukes big enough to do what Bruce Willis did in Armageddon? So yes, for real asteroid threats, if we just launched another Starfish Prime on, say, a Delta II rocket, the grandchild of the Thor, would it be big enough? Could we even save ourselves with a nuke? Even if we got approval and all that stuff? The answer is it really depends, which I know is a non-answer, but I'll get into it. It's the asteroid size and the time to impact. And not just for the logistics of getting the paperwork signed, there's actually a practical reason time to impact is important. What's the Armageddon scenario? They said an asteroid the size of Texas. Texas is 790 miles wide. The dwarf planet Ceres, visible from Earth and classified as a planet for nearly a century, is only 590 miles wide. Clearly big enough to achieve the round planet state, so to speak, the state of Texas. So it's really big, really big. Remember, that how big was the one that took out the dinosaurs? If that's a 100-mile wide crater, you divide it by 25, it's about 4 miles. Caused the extinction of most of the large animals on the planet. 4 miles. This movie proposed 790 miles. If you do that calculation forward, multiply that by 25, you get like a 15,000 mile wide crater, which, well, now you're just obliterating the Earth, right? So I think the movie got that part a little wrong. And so let's carry it forward then. Let's just say that Ceres is going to hit us in this movie. And we take the largest nuke ever tested, Tsar Bomba in Russia, 50 megatons. That's the size of our biggest nuke's crater on the surface of that red dot. It would require 2 billion 50 megaton nukes to adequately destroy this world. So, being that that's not in anyone's arsenal, even though we do have a lot of nukes, yeah, we say now that a 2-mile wide asteroid is a civilization crippler. So, no. Given the scenario in this movie, nothing could have saved us. The asteroid is way too big. Oh, so big, it's almost no way we wouldn't have seen it. And no, it doesn't matter how far down you drill. It's kind of like saying, well, did we blow up the Earth with all the subsurface shots we did here? No, the ground went, and then a bubble formed, and then the bubble collapsed. I mean, clearly, look at Ceres. If that's the biggest nuke crater, look at all the other craters already on Ceres, like 2 times to 5 times the size. So, no, that won't work for Ceres. Yes, sir?
Would a blast that big be able to push it off?
That's an interesting, now, that's so big, the answer is no. But you're pulling on exactly the right thread. We can't blow it up. Could we do something like push it instead? So you're actually jumping forward in my talk. It's a nice softball, thank you. So the good news is, well, how realistic is that Texas-sized Ceres, the brother that we never knew about coming to hit us kind of scenario? As of now, because we've been looking for a while, there are even congressional mandates that NASA find this stuff. So this has been getting real. In 2005, Congress mandated NASA has to find all asteroids larger than 0.6 miles in diameter, better than 90%. Prove it statistically. And you can do that by looking at the moon and frequency of impacts and et cetera, et cetera. We feel pretty good now that we definitely know where everything with a little margin of error, but everything larger than 0.6 miles is. And that's not stuff that's going to hit us, that's just where it is. Anything that's in Earth's proximity. So the odds of an Armageddon surprise, they're 0. I mean, scientifically it would say near 0, but nah, I wouldn't buy it, because there are other things too. Everything tends to flatten out in the plane of the solar. Since things are spinning, it's like pizza dough. So you throw the dough up and it's spinning and it flattens out into a pancake. That's why I always joke, people talk about there will be a planetary alignment. And I'm going, well yeah, there's the plane of the solar system like the pizza dough. If the planets aren't aligned, there's a really big problem. Like planetary alignments are normal, we just end up seeing, so yes, everything orbits in the pizza dough plane. So yeah, I think people get that. People think something's going to happen if they are aligned. I say no, get really worried if they're not. So, like the gentleman mentioned, there's more than one way to nuke. So, okay, what's NASA been up to for planetary defense since Chelyabinsk? Well, even before Chelyabinsk, they were doing what they call the Asteroid Redirect Mission, or ARM, something that I really liked. And their plan was actually to go to one of these near-Earth asteroids, grab it, and maneuver it into orbit around the moon. A very broad orbit. But we'd essentially bring the sample to, it's already going by anyway. It's the equivalent of just nudging it a little on the way by, and you bring it into a lunar orbit. Now the whoops, they did that because if you go whoops in your calculations and putting it into Earth orbit, you've created an extinction event. Whereas here, if you go whoops, it might crash into the moon, but even that, they've kept this very distant. So what was this all about? It started out as a plan to bag, find a small size asteroid. Remember, something 60 feet wide can make an enormous crater. So yeah, grab one of these 20, 30 foot wide asteroids, sort of dock with it with this big ugly bag, and then use your thrusters to just gently take it with you and park it around the moon. So I thought this was amazingly cool. It included astronaut exploration from NASA's new Orion spacecraft, and it did not require a lander, not to get into space stuff, but this is the mission humans could do now, with the tech we have now, and actually explore something. Until we have a lander, we've got this Orion spaceship, and we're going to go around the moon, but we can't actually walk on anything here. Yeah, we can crawl and touch something and get samples. Okay, well, then politics got involved, and budget requests started getting denied, and what would this have done? It would have given us the technology to maneuver an asteroid. We would have actually proved it, meaning for science, or protection, or mining, or anything. So I thought the trickle-down value from this would be enormous. Well, then a couple years later, it scaled down with, okay, we'll send a robot ship out to grab a boulder from the surface of a near-Earth asteroid. It's like, okay, in the same plan, park it in lunar orbit, and then we go visit it. And then, finally, with the new budget request in 2017, there's a lot of cool stuff in it. NASA did get a boost in their budget, but this was canceled, which made me very sad. But what did they do instead? In the last year, they opened up the Planetary Defense Coordination Office. And this is a partnership with the National Nuclear Security Administration, with the national labs. They actually have people who make and design nukes on board in this office because they're also the ones who understand impacts, craters created by impacts or explosions, and then nuclear emergency response. How do you deal with an explosion going on? Well, the way you respond to a nuke is actually going off in a town is very similar to how you respond to an asteroid hitting a town, with the radiological differences. But anyway, turns out a lot of the math had been done. But these guys are promoting a newer idea than the asteroid redirect. They call it the Hypervelocity Asteroid Intercept Vehicle, HAIV. And what this thing is, it's a 1-2 punch from what they call a leader spacecraft with all the eyes and ears on it, and then the follower, which actually has a nuke. It is a nuke. How does it work? Well, the scientists, we realized speed is a weapon too. Why does an asteroid, which has no warhead, it's just a dumb rock. There was actually a whole strategic defense initiative, a Star Wars plan called Brilliant Pebbles, which is code for smart rocks, where we actually launched just dumb slugs of rock at enemy satellites. It's very effective for this reason. Why does a rock, how can it explode with the force of a nuke? Speed. I mean, you rub your hands together a little bit and it gets hot. Imagine if you're moving at 66,000 miles an hour. You come in here, the ground doesn't know what to do with all the energy, and everything vaporizes, and then it explodes because you vaporize, the air can't hold it, etc., etc. So, whenever space guys spend so much time trying to think about how do we slow down a spacecraft so that we don't hit an asteroid we're trying to study. Somebody finally went, wait a minute, we spent all this time and energy getting that spacecraft going fast. Maybe we can use that too. So, how does it work? Step one, you launch it. And I notice there's a mathematical relationship. Every kiloton blast you want equates to about a kilogram of launch mass. What does that mean? That means for 300 kilotons, the Delta II, which is like the modern Thor rocket, will do it. Okay, to asteroid approach velocity. When you want to go to somewhere in space, it's all about speed. So you can't just go in a straight line and get where you want to go. It's actually mystifying to people who haven't worked on it. How do I phrase this? If you're in orbit, that means that you're going as fast around, like the Earth is always pulling you down, right? Earth always hits me down. So imagine I fired a bullet and it went, and it hits the ground there. Imagine I fired a little faster, it goes farther before it hits the ground. Imagine I fire a bullet so fast that it falls at the same rate that the Earth is curving out from under it. That's orbit. You could orbit the Earth at 3 feet off the ground if nothing was in the way and it didn't blow up because the air was in the way and all that stuff. But orbit's nothing special. Orbit is just speed. So how fast do you have to go to cross enough Earth so that by the time you fall, the Earth is curved that same amount? Well, I mean, just think about it. How far do you have to go for the Earth to drop away from you that fast? So anything in our orbit is going really fast. It's about 5 kilometers per second. Sorry for kilometers. It's a standard unit. I can go to miles per hour sometime. But anyway, there's enough speed. This rocket can get something going fast enough to get up to the speed of where the asteroids are farther away. And you might need newer rockets to get a megaton thing up there. But now at least we can see we're playing with that same reality space. We can make a nuke that small. We do have rockets that can go that fast. And so what happens? This thing, with our follower, with all the eyes and ears on it, one day before impact, they separate. And they're going real fast. 45,000 miles per hour compared to the asteroid. And the leader gets ahead with its impact sensor. This is where things get really interesting. This thing at 45,000 miles an hour will get to the asteroid, and at the moment its sensor touches the surface, contact, it sends the arm signal to the nuclear warhead. And this is where it gets interesting, because really they're less than a second behind each other. Well, that leader, just the mass of that leader is going fast enough to make a huge crater. Now, less than a second later, the armed follower spacecraft with the warhead, armed warhead, goes into the crater and right in the gaping wound blows up. So think of it like a super drill. In the movie Armageddon, the whole premise is we have to send drillers because we need someone to make a hole in this asteroid so we can blow it apart. Fragmenting an asteroid, well, that's a fair idea if you do it back far enough. But somebody realized we don't need drillers and a drill to do it. The spacecraft's already going fast enough. If you just fling anything into the surface of that asteroid at 45,000 miles an hour, it's going to make a big hole. And then the nuke is naturally following it in, and it blows up, fragmenting the asteroid and saving the day. So that, hopefully then, turns what might have been a civilization-ending event into, at worst, if you catch it soon enough. So you need to give it like the shotgun blast. The buckshot's got to spread out. So if I fire a shotgun at something 1 foot away, it's going to get hit by everything. If it's 100 feet away, it might not even get hit by a bead. Same idea here. So if you fragment this thing early, everything spreads out, and you might miss the Earth altogether. So you can turn a civilization ender into maybe just a series of bad days. You haven't destroyed civilization. You've injured thousands of people and broken a lot of windshields and ruined a lot of car alarms. So, which is not good, but much better. Okay, well, I'd like to say, well, there's more than one way to nuke something. So what if this stuff isn't ready? What if we find something tomorrow? Because the technological development level on that stuff still has a ways to go. Is there some other nuclear tool in the toolbox that we can dust off and use? Well, yes, there's one that hits a little closer to home, which this was renamed the Nevada Research and Development Area, but the reason that there's a rocket with electron orbitals around it is in these faint letters. This is Area 25 in the Nevada test site. You can just make out this is Nuclear Rocket Development Station. And it's been covered over with stars, and depressingly enough, this sign has been destroyed. There was a series of, recently, last year, there was a big storm that came through, wiped out Latham Wells Road, a lot of repairs going on, and it obliterated this top part. Half of that fell off, and this whole panel with the rocket is gone. And there are fragments all over so that was the coolest part of the sign. But anyway, yes, technology is called NERVA, and I got a whole other, I'm gonna have to try and help myself not talk too long on this, because this is one of my favorite topics there are. What is NERVA? It's technology developed here in the state of Nevada. It was pioneered under what they called Rover at Los Alamos and migrated here to really turn into something real. And in the 1960s, they developed this technology, and it was ready for a flight test called RIFT, the Reactor in Flight Test, by at least 1972. It kept getting pushed. What is it? It's actually very simple. People assume that nuclear technology is intrinsically complicated. It's not. Nuclear thermal propulsion is about the simplest rocket that you can make. It's a heat rocket. It doesn't burn anything. You take a very cold fuel, and the temperature is the important part. The coldest fuel you can find, liquid hydrogen. You simply make it hot and let it go out of a nozzle. That's it. Now, I mean, there's mechanics involved. You have to have turbo cryo pumps and all that stuff that, to move, because this stuff is so cold, it's as cold as you can get something in the universe that we know of so far. But why is this so special? Well, because it only uses one propellant instead of two to achieve the same thrust. You can basically cut your fuel in half for the same amount of thrust. It's really cool. So what does that mean? It means it's twice as powerful. We have more sophisticated rockets today, sure, but they're still using chemical bipropellants. So this NERVA technology is twice as powerful. They call it specific impulse. It's got twice, upwards of 1,000 seconds, twice the specific impulse as our best rockets today, half a century later. And we brought it all the way up to flight. And I should say all the way up to, so this is a picture of Test Cell C, which is basically a rocket all splayed out on the ground in a building. And you can take a rail car, and these rail cars have been preserved. Locomotive 1 and 2 are on display at the Boulder City Railroad Museum, just across the way. You can reach out and touch these guys. They wheeled nuclear rocket motors, test versions, across the Jackass Western Railway. It only existed on the Nevada test site. And they would park with these test cells, which are rockets all laid out, test, retreat, go back to maintenance, assembly, and disassembly buildings. And where did it go? And they did this all so fast. It started in the early 60s, and by 70, they took this idea on paper. There's a picture of it in test, and now here, they built a rocket engine test stand. The tests fired upward because they were on the rail car. So it was just easy that way. You weren't like firing down in your own rail car, destroying your own train while you're performing the test. So finally, they got to a point with the XE series, they called them. Flipped it right side up so it's in rocket configuration. They have a big flame trench underneath, and they let these things go, and they produced megawatts of power. I mean, you need Hoover Dam stuff to normally do that. And what does it mean? It means they proved thrust. They proved the technology, and there were no problems with the reactor. I mean, of course, they did all this without computer modeling in the days, for the most part, with really long punch card models and stuff. But they, there were some things broke, but they were testing. So by the end, things were not breaking; they were functioning beautifully. And it got so serious, Marshall Space Flight Center in 1970 developed Werner von Braun developed an entire mission series. This is how you take the upper part of a Saturn V that took us to the moon and take us to Mars. Then, and put a base on the moon. Then, it's the same size rocket, and this stuff was ready to go at several levels. So, and then I should say, well, what happened? Why isn't it there? That's from my other talk. It's all Nixon's fault. Basically, he had a I say that non-politically, he had two options in front of him. Just they're limited dollars. What do? Waning support for Apollo. People are getting tired somehow of watching people walk on the moon. And so you've got this, which was started by Kennedy, and this was the follow-on Apollo Mars program. And then in his other hand was this thing that was supposed to break open space. And it was going to give us all this revolutionary technology like global positioning, global communications, global transmissions of video and sound, and global awareness, photography. And it did. It was called the Space Shuttle. And we did have rapid access to low Earth orbit, and we did develop a lot of technologies. But it came at the cost of maybe putting a flag on us. So I like to think that it's ironic that if Nixon had gone the other way, we might have giant brick cell phones today, but there would be a base on the moon. So it's the world that might have been. And we'd also be using maps and telephone books to get where we want to go, as opposed to like this computer in our hand. Anyway, so what if? What if we could just stick a Nerva motor to an asteroid? So we nuke it, but not blow it up. Nuke it in that we use a nuclear thermal thruster and push it out of the way. Okay, but could we? Certainly we'd have to warm up a lot of expertise, but we've done it before. And now we have more tools in the toolbox to build things. Well, what about the nuts and bolts? Can we even orbit an asteroid with precision? And can we, dock with it? Well, as it turns out, in 2001, yes, there's a near mission to an asteroid 433 Eros. It was so successful, this asteroid's tiny. We parked a spaceship in its gravity. This little microgravity field. They just orbited for years, took all the pictures, and it was so successful, they did everything that they wanted to do with it. And then they thought, well, now what do we do? I mean, normally something breaks, and then the mission's over, but the thing was still working. And there was one guy who said, I bet you I could land that thing. And so all that was left was maneuvering thrusters. It was never intended to be a lander. It had no feet, but they did it. They programmed it in, and this is the landing sequence of photos. And here, at like the boulder level with shadows, is the last picture we got out of near. And then it transmitted data for a while, and then finally, its solar panels weren't pointed to the sun anymore, and it gave up. But yes, we can intercept, orbit, and land something that's not even designed to do that, and that was 16 years ago. Now, in 2014, the European Space Agency did it even better. We intercepted a comet, and Rosetta landed on it, and this one did have legs. And this is a picture from Rosetta sitting on the surface of a comet, which is probably what blew up over Tunguska. Not this one, of course, but same idea. So, okay, can we get to one? So we proved the technology went up to flight-ish in 1970, and we can find, track, orbit, and land on something. So the distance between pushing something out of the way with nuclear thermal and now is not far. We're close. Now, that asteroid redirect mission sure would have helped here as the missing link, actually docking with grappling an asteroid. But, enough griping about that. So where does this take us? You might have seen the word Apophis in the news. There's an asteroid called 99942 Apophis that keeps showing up. Why? It's one of the usual suspects that crosses our orbit. And some news outlets, most of the time the less reputable ones, get a hold of some NASA report that says there is a finite probability of an impact in the year 2024 or 2039. And the headlines are, Apophis will hit the Earth. And everyone gets excited and then go, oh, well, it's not going to hit the Earth. Okay. And then it's like clickbait. Well, this clickbait keeps showing up. And it just showed up like 2 days ago. I was getting ready for this talk. It is in a near Earth orbit. It's bigger, 1,200 foot diameter. That's a real size there. It would leave nearly a mile wide crater. That's bigger than Meteor Crater in Arizona, about the same kind of scale. And there is, yes, a slim possibility of a strike in 2039. When I say slim, I mean astronomically slim, pun intended. It has to do something really special on its next approach that'll put it in the right position for the next approach, and this. So is it going to hit us? Probably not. But and here's a rendering of its orbit. The green circle is Earth, and the red circle is Apophis. So you can see it's got a very It's a similar period, and it's got a lengthy cross-section. So this makes it, in my mind, a prime target for testing some of this stuff. There's a name. We know where it is. We know how big it is. And NASA, European Space Agency, and others, they've looked at this for exactly those reasons. MIT, just this year, I think it was just this month, proposed, I think, CubeSat scale, a small mission to actually go check it out during a coming flyby, collect some of the missing pieces of data that we need to actually, land on this thing. So I'd say, let's try some of this stuff out. Target Apophis. So one of the words I want you to walk away with, is there a real asteroid threat? Yes. Yes, there is. And not just hypothetically, real. It hurt 1,500 people just a couple years ago. So yes, it happens. Now, at this level, might you treat it like a volcano? Sure. Or an earthquake? Sure. But there are codes. There are laws. There are distances and warning nets and all sorts of infrastructure that we've legitimately set up to protect people. So yes, it's legitimate. Now, can we even nuke anything in space? Oh yeah. Not a lot of people know about it, but there were spectacular tests that demonstrated us doing this. Because after all, the ICBMs that we pointed at Russia and Russia pointed at us were the exact same rockets that took us to space. So they're the same rockets. That's Wernher von Braun, the grandfather of basically everyone's rocket program. When they tested the V2 rocket, he said, because in his mind, he was a space geek all along. I mean, he developed it as under a weapons program for the Germans. But when they tested the V2 and it actually went somewhere, he said, well, the spaceship performed perfectly. It only landed on the wrong planet. So perhaps a little naive of how his stuff would be used, his head was clearly in this space all the time. So yes, rockets are rockets. Send them up or down or wherever. Would it work then? So if the threat is real, and if we can nuke something in space, would a nuke work? The answer is maybe. For something hundreds of feet wide, sure. We can blast that thing to smithereens and turn it into a pile of little cloud with small glass droplets that'll make a spectacular but harmless meteor shower on the way by. Okay. What about miles wide asteroids? Yes. This is where time is key. We have time to park a Nerva motor on the side and move it out of the way, for instance. We have time to find a weak spot and do that 1-2 leader follower nuke approach and fragment it. Yeah, okay, yes, but time is critical. What about hundreds of miles wide asteroids? No, those are worlds at that point. It's like getting smashed by the leading hypothesis for why the moon is here. There's strange things about the moon, basically. It's missing all the core stuff, and it's missing all the atmosphere stuff. It's just everything in the middle, which was a puzzle for a long time. That's actually what the Apollo guys found. They took samples from the moon and brought it back, and we started piecing together, well, what's going on with the moon? And, well, it's also got it orbits the wrong way, and it's going out farther with time instead of in. The only moon that does that. Most moons get slowly dragged in, and they crash and make spectacular rings, like Saturn. Saturn's rings used to be a moon. But there's one model that matches the moon. There's one way to do that. To do something where you miss the light stuff and the heavy stuff, and you get just the middle stuff going the wrong way. If you smash Earth with a huge world early, the Earth catches all the heavy stuff, all the light stuff is flung out to space, and you've got basically this floating epitaph that cools and collects together in orbit, and then you have the moon. So yes, the only thing that makes sense for creating the moon, which the Apollo missions actually help confirm, is getting smashed by something like this. So yes, if we want to completely reset the world and make a new moon, maybe, sure, something hundreds of miles wide. But, no, the movie totally doesn't work. Remember, this is the impact crater, or the explosion crater from the largest nuke we've ever made on something smaller than what the movie proposed. But the good news is we know where all those things are, especially the really big ones. I mean, when we say we know better than 90% for everything larger than half a mile, we mean, okay, maybe there's something a mile wide out there. There's nothing like they would have found this in the 1800s. They would have found it. So anyway, no, won't work. But what if there were? What if somehow we did miss the Armageddon, Texas thing? Well, maybe it makes more sense to push it out of the way using maybe the other nukes developed at the Nevada test site. rather than try and blow it up. And there's another one I didn't put here at the end of the slide, which is Orion, which nuclearly basically explode tiny nukes as propulsion. You put a big shield plate in front. Now, if somehow we were cozy with some nation sending up basically a giant space jar filled with hundreds of tiny nukes, if you get over that hurdle, then yeah, that technology actually made it a ways, and that would work at moving something out of the way too. So not just one, but many over time. Yes, sir.
Are we advancing with our lasers?
That's an interesting. So that's a great question. There's a propulsion method called a light sail, which basically you can use consolidated photons to produce thrust, basically a laser beam, and it would require putting the laser emitter somewhere else. Like you can't. That's the whole. You can't stand in a ship and blow on your own sail and create thrust out of it and move a boat. So if from the Earth maybe we can beam an asteroid with a huge laser, yeah, hypothetically, there's actually something called the Poynting-Robertson effect, which is the sun doing that. So just how fast it rotates any asteroid, the sun hitting one side preferentially than another, and the difference in the rate that it emits infrared versus its hitting, you can actually move asteroid, but it takes even with something as powerful as the sun, it takes 100 million years to move something. So in principle, excellent. In practice, I don't think we can make a laser that big to really do that, but you're definitely pulling on the right threads. So there you go. That's the long and short of it, nuking asteroids. Thank you very much. Question over here? You sure? You can? It's all right. Sometimes you don't have to either. Yeah, yes, sir.
How many different densities are different, meteorites and asteroids?
Yeah. Excellent question. The question is how many densities are available amongst all the different kinds of asteroids and comets? And the answer is how many densities of rock are there on Earth? It's a huge spread. Now, most of the lighter stuff tends to burn up through our thick atmosphere, which is why we tend to find more iron meteorites. And then the stony stuff isn't as obvious, so it's harder to see. But not only is the density of the material widely variable, but it's also the overall density of the object. By that I mean some asteroids that are one type, pick one, the material has a certain density, and it's one solid mass. Versus a different asteroid will be made of the same material, but it's more like a loosely consolidated pile of rubble. So being able to tell the difference between the two, you can blow apart a rubble pile pretty easily. If it's one solid rock, like iron, nickel, rock, you're gonna have a hard time blasting anything apart. So that's part of what asteroid guys are working on right now is, because they would look the same from here, it's the same material. So if we try and do something like spectroscopy or look at the moon, it's hard to tell whether it's a rubble pile or whether it's a solid rock. And then you've got to worry about, which kind of rock is it made out of? And then it's all over the place.
In theory, if the asteroid belt being like a planet that blew up, does that make sense?
Now, at this point, it's a lot messier than that. So the asteroid, what we found, like I said, there's evidence of 80 fingerprints in there, sprinkled around. And so 4 Vesta didn't come from Ceres. And so we're finding discrete, separate geology, basically, for a lot of different groups. So that the asteroids tend to hover in clouds, like they're families, they call it. And they all tend to have unique geology. And basically, because there's so little of the original material left, there were lots of worlds that got obliterated, and there was stuff all over the place. And now think of it that way, it's just a shrapnel field across the solar system, and now, many, many eons later, the only ones left are in these little tide pools created by Jupiter, where it's made these little gravity-safe spaces. And we know that, this is devil in the detail stuff, but as soon as if something pushes an asteroid out of one of those safe spaces, it gets ejected quickly. They call them Kirkwood gas. And they're all, if you talk about the math in the universe, they're all resonance-based. So any distance that orbits at a frequency like 2 to 3, or 4 to 5, or 5 to 7, that's what makes, like someone pushing someone on the swing. It doesn't matter how fast the person on the swing started. If you just push like this in the air near them, and they hit you every once in a while, you're going to slow them down when they come in and speed them up when so if you keep doing this, eventually they will be swinging at the exact rate that you push your arm. So now think of Jupiter as a shove. And so what happens is it will collect everything into these resonances that are shepherded by Jupiter, just like shoving on a swing set. And then if anything falls out of that, it gets flung into the sun, basically. So it's cool where we find these clusters of asteroids, and there are gaps. Again, it's a cool thing to see. If you Google Kirkwood Gap, you'll see as you move from the sun out toward Jupiter, in distance-wise now, just straight from the sun out, there will be asteroids and then no asteroids, like a sprite of nothing, and then asteroids and a sprite of nothing. And someone did the math and figured out that they were harmonics. It's like music. It's gravity resonance with Jupiter's orbit and distances from Jupiter. It's because Jupiter's the big brother of the solar system. So, yeah, there's evidence not just of one planet was broken apart, but many. And further, they had to be planets or worlds, because that's the way you get the iron to sink together and the crust stuff to come out, and then for it to cool off and form those minerals. It had to be not only a world, but a world long enough for it to differentiate and become round. So we can know all that just based on what minerals are there or aren't. And then you can compare that against that fourth type, which is the original stuff, which is just this conglomerate of nebula junk from way back. But no, that's an excellent question. Yes, sir.
If asteroid came into the Earth's atmosphere, would Jupiter affect it at all?
Ooh. If an asteroid, the question is, if an asteroid came into the Earth's atmosphere, would Jupiter affect it? At that point, it's too late for Jupiter to help us. But your question may be right one step upstream, that we may have Jupiter to blame for it. Because sometimes, that's why you saw the big explosion on Jupiter the size of the Earth, that's why that thing hit Jupiter. It just got too close, and Jupiter changed its path, and it swung right around and hit itself. That could happen against us. Something could get too close to Jupiter and swing right toward us. So, yeah, he protects us most of the time, but occasionally he may be responsible for sending stuff our way. That's a great question. Yes, ma'am.
How young were you when you decided this was going to be your passion?
How young was I when I decided? I've always naturally gravitated toward it. I mean, as long as I can remember, really. I've always been into, space and science fiction. And, I didn't know I was going to drift geology, but as it turns out, when I got older, I realized I like being outside. I didn't want to be stuck at a computer for my entire career. I like that sometimes, but I want to get the data and then reduce the data. I want to do the whole. But no, basically, it's just me. I've liked this stuff since way back.
Thank you. And one other
Sure.
real quick one. Studying meteor crater in Arizona today, is there any value in still doing that?
Yes, and there is economic value in doing that. What we found recently, whenever you have something blow up with that much force and that much heat, you remelt, you create a whole spectrum of new minerals. And you can get pressure melting. There are diamond layers that have been associated with asteroid impacts. The same way that geologists, when we really got familiar with oil deposits, you would look for certain things that would be indicators that that's where you could trap petroleum, anticlines and things that get. In the same way, there are prospectors now studying more seriously how asteroid impacts have shocked things and consolidated things. There's a platinum deposit too, with little platinum crystals. The Condor Massif, I think over in Siberia. Yeah. That also, if it was a crater from an impact, you've got minerals that may be precious that were created as a result or in association with the fact that there was an asteroid strike there. So that's a great question. And there's still all the science, if people still go in and take a look. It's got a lot of value as a field aid. So we can look at this in books all the time. But if you want to, they took the Apollo astronauts to Meteor Crater, and they took them to all of what they call the plowshare sites out on the Nevada test site, which are ejection craters, where you try not the subsidence craters where you made a bubble underground and it just fell. But if you actually ejected material, those are identical to craters on the moon. And the reason specifically I call the test site the most moon-like place on Earth is because unlike Meteor Crater, and unlike any crater elsewhere on the Earth, our craters out on the site have something in common with the moon, uniquely in the whole world. They're sharp. All craters on the moon are sharp. All of them are trying to rip your spacesuit. Why? There's no air, there's no erosion. Not really. So, if you want to train logistics for moving around moon craters, the test site is the best place to do it. Things like Schooner Crater. Yeah, great question. Yes, sir. Or either.
I have two questions. You mentioned that an asteroid can be rubble.
Yes.
So, and we cannot really detect it from Earth. So what would happen if we are sending a nuke to the asteroid and we are wrong with our assessment?
That's an excellent question. That's one of the failures, the failure modes of a nuke. If we blew up a nuke in a gravel pile, you could look at it as I could bring it back to the site. If you've seen in the museum pictures of Sedan Crater and pictures of Schooner Crater, way up in the northwest, the difference between the two is Sedan was blown up in alluvium, in loose dirt, whereas Schooner was blown up in hard rock. And what do you see is different? Schooner, you've ejected blocks the size of houses, and efficiently. Sedan, a lot of the material went whoop and came right back and slumped. It was very sloughy. And so by the same argument, I mean, you could go two ways. I mean, you could, and this is where the physics is so important. I guess I should qualify myself. I see it as a failure mode, where you could get force distributed throughout the asteroid. It's able to, sort of like liquefaction, it's able to jiggle more and use up more force that way, as opposed to actually breaking. And so you may smear it or change it, but not blow it apart if it's rubble. Versus hard rock, you crack that, and if it breaks, yes, you've got some. Now it has to break, but you have to do your math right. But you know, the other side, of course, the door is cracked for. Oh, if it's a rubble pile, maybe it all it's so loosely compacted that it just kind of you nudge it and it flies apart. We don't know. That's why we need to get our hands on something real and actually do some. Get away from the telescope and put boots on these things.
The second question is now, what has the biggest impact on I mean, there's a momentum transfer, there's a force, and there's energy. So what is really then responsible for an impact of kind that we have, that is not of any danger for us anymore? I mean, it's momentum transfer is, we would probably push it away. That force would only be relevant if there is a constant push, right? Then the other way would be energy, right? That we are really, yeah.
Yeah. Okay. Well,
what is now the relevant aspect?
the nuts and bolts of the physics. So this is nuance here. The difference between momentum and force and energy are real, but they're all related. So if I understand you right, I would say the driving motivator, like the most important factor, is force. We have to change the delta velocity of that object. We have to. So via force, it's not momentum transfer, it's force. The constant application of force, and then you would end up in a
But we have the interaction happens via radiation. So
so specifically, sorry, I mean, I was talking whether you're pushing on it with a nuclear thermal motor or you're hitting it with a
nuke.
Oh, you're hitting it with a nuke. Ooh. You still need to fragment it. So that's a good question. Well, it's less the energy. And so if you had to rank them, it's more momentum transfer and force. But from that perspective, like what part of the nuclear explosion are you most interested in harnessing to fracture the world? It's not just important that it breaks, it has to fragment. So in that case, you need to change momentum of the pieces. So you need force to exceed the failure point of those minerals. So you need to break it with the force. And then you need enough momentum transfer left over to move the pieces apart. It doesn't have to be fast.
So then it is a lot of theory of if this is really working, because we have the only only transfer happens through radiation. And now we have to understand then what absorption of radiation happens in each of these different materials.
Yeah, oh yeah. Yeah, I mean, it would be a lot of really cool research to perform, and we may find a way of mining it. The events that we already that you're kind of illuminating new value potentially in the bedrock or alluvium plowshare sites. So it's an excellent question. Yeah. Yes, sir.
So who has to take point on this asteroid killer idea? Is it NASA, or is it going to be the UN Office of Outer Space Affairs, or is the Russians doing it now that they got hit with one, or like what's?
Yeah, so I will give you my honest answer, which is exactly the same answer when people ask, well, what about people who are going to mine an asteroid or set up a mining base on the moon? Who regulates that? Who's going to give the license for them to do that? The real answer is, how do I turn this inside out?
Bigelow.
No, yeah, right now. The people who go first make the rules. So, that's the honest answer. The people who do it first make the rules. So, if Russia decides to go first, and they've already talked about retrofitting ICBMs for asteroid intercept, if they do it first and they decide we're going to try and save humanity, even if the UN writes them a very nasty letter and says no, they're not going to run out and catch the rocket, and that's already 100 million miles away. So, especially with this kind of stuff, because there's no teeth on any of it's all pen and paper. So, really, I mean, it would be akin. I mean, it's very similar to how there were international condemnations of the above-ground nuclear tests. That did not, no matter how many condemnations there were, eventually there's enough political momentum to do something. But it didn't stop any of the nuke tests until there was like a global uproar. So I envision an exact similar scenario that a lot of this will just happen when somebody does it. And based on what happens and the international response, then we'll see the lines in the sand get firmed up and concreted and things like that. Same with mining. So on paper, who's supposed to govern it? Well, the UN would say the UN. And the US says, if it's a threat to US sovereignty, it's under our purview as a sovereignty. And the Russia would say, well, if it's a threat to us, I mean, they could even anyone could fudge numbers and say, we think that it's going to hit sovereign soil, therefore we're going to take care of it, even though it's a global event. So you can make very sensible legal arguments across the board. So honestly, I think it'll be just like going to the moon, and it'll be just like the nuclear tests. It's the people who do it first make the rules until they get shouted down by the rest of the world, if that happens, and then they'll change their tune.
It takes money. Does Russia have the money for this?
The technology is they already have a stockpile, they already have rockets. So that's what I was trying to show, is that many of the bits and pieces to do at least rudimentary versions of this are already here. So yeah, if they've got money for their weapons modernization program that they've been playing around with, so I read, yeah, I think they've definitely got money for this, if they wanted to. And then of course there's the question of weaponizing space, and is it really an asteroid intercept missile, or is it a missile parked up there and waiting to come back? Great question. Yes, sir.
In terms of like common debris Earth catches from smaller asteroids,
Yes.
how does space station navigate not getting hit by one and not getting ourselves?
The real answer to that question? They don't. Now let me pull the question was, if there's so much small-scale meteoritic dust and small little meteorites hitting Earth all the time, 7 Volkswagen buses per hour, how does the space station avoid getting hit? How do our satellites avoid getting hit? And what I want to show you, I have no idea if this is actually going to, if this is online or not, but there was a satellite sent up called LDEF, the Long Duration Exposure Facility. And its whole purpose was to place materials out into space it was in the bay, this is another thing the shuttle gave us, and So here's a, well, it's not great, but it's something. Here's a picture of LDEF. It's big. So these are all panels of different material. And they let them sit up there for a long time. It was more than a year, I think. And then they brought it back, and they put it under a microscope. And what did they find? They found that, oh, come on, you're robbing my payoff, Google. LDEF, gotta be I won't spend 1,000 years looking at this, but there's if I can find just a shot of one of those panels, it's really eye-opening. LDEF, panel, and yes, here we go. There we go. So in only a year, that's one of the panels. I don't know if you guys can see this. Each one of those dots, that's an impact. So what does the space station do? They have something called a Whipple shield. They actually have a layer of stopping material and an aluminum plate. They've done the math and said for most of that stuff, it'll take it. It'll be okay. But astronauts are kept up at night by hearing bang, ding, bang. Like the stuff you never hear about is every once in a while. And the one that really disturbed me, so they're getting hit. So basically they just budget their shielding to take the average dust size and stuff. And I'll show you one more thing that proves it. A cupola window. So if you guys, there was this new window. Not that. International Space Station. I can walk and chew bubble gum at the same time. I can walk and chew. Okay, so they installed this beautiful series of windows. It's where it was years ago, and it is where most of the best images of it. So if you've seen any new NASA stuff the astronauts are taking on, putting on Instagram or Facebook, it's coming from the cupola. And what I want to show you is I bet you if I pull up any cupola image, pick one, I'll pick this one, and I look at it in full size, look at all those pock marks on any window. Streaks, pock marks, these things are getting pummeled and nobody talks about it. Little crack here, dot there, crack here, da, 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 da. Those scratches are coming from the inside. So the answer is this is some of the stuff that NASA doesn't talk about, but it's proof that it's real. And what they do is from LDEF, which is back in the 80s, they now know what their worst cases were and what the normal is, and they just size these windows to take it. But that's also why you'll notice when you'll see pictures when there aren't astronauts using it, they have big aluminum covers that close over the outside of that thing. So this is even during the periods of time when the shutters are open, which is even less than all the time. So great question, and this is a real threat for astronauts that they don't broadcast. Yeah, I mean, it's cool. I mean, you have to really believe that the engineer who designed that window did a good job, didn't use the wrong multiplier or something. But yeah, I thought it was terrifying when I first found it. And I was like, wait a minute, any cupola window at full resolution, you could just see all the little dots, and these things were perfectly aerospace clear when they were launched. But anyway, sorry to digress, but that was an excellent question. Anything? Yes, sir.
Question about your nuclear rocket theory.
Yes.
How do you adjust for the rotation of the asteroid?
Devil in the details. Yep. So the question is, hey, wait a minute, Ben. This is a really nice sketch you laid out for us here, but don't all asteroids rotate? So if you put a rocket on one side, isn't it just going to not do what you want it to do? The way to get around that is, you certainly have to account for it, and the rocket's not going to do it. There are too many axes of movement, I don't think you'd ever really, you couldn't rendezvous and land. There are too many unknowns. But what you can do is, how does the space station stay level? They always keep it facing Earth. It's the same orientation, Earth down, nadir toward the Earth. How? How doesn't it drift? Well, in the public, they said thrusters. There aren't thrusters going off all the time on the space station. I call them CMGs. They're giant gyroscopes. And you got a computer system that senses what your rotation is and where you want to be, and they wheel those things, and you use the centrifugal pseudo-force to your advantage, and you bend that thing using the force of physics to the right orientation. So if it were me, and you're asking me, well, how do you stabilize an asteroid so you can park a nervo motor on it, I'd say two things. Either you send a precursor mission with some CMGs on it, park that, stabilize your asteroid, or you put a CMG package in the motor, assuming you can like grapple with it enough, and not, the risk would be then like breaking off the fingers of however you're attached to the asteroid. But no, you have to deal with it, and the rocket's not going to do it by itself. So I would say CMG. Yeah, I'd say do CMG stuff. No, they do. Yeah, what happens if you adjust the momentum? Now, the mass is probably too big. Like a CMG, if the rotation's not a lot, yeah, CMG could probably stabilize it. But actually deflect the asteroid? No. But the B612 Foundation has a simple deflection tactic that's similar to the nuclear rocket, but even less complicated, mutual attraction. So technically I'm pulling on the Earth at the same time the Earth's pulling on me, right? I'm just exerting a teeny tiny force in here, so it's overwhelmed. But if we were in space and it was just two of us, we'd be attracting each other with equal force. Well, what if you park a heavy spacecraft next to an asteroid and you use thrusters to maintain a constant altitude? You're going to drag that asteroid over just based on the spaceship's gravity field. Call it a gravity tractor. And I think that's the version of what you're talking about that I think is actually on the books is, just park a huge something next to the asteroid and let it drag it out of the way, and then you don't even have to worry about the spin. But that takes time. That's a slow process. So the question is, what if you need to do something fast? And that's where I think something more energetic would be useful. Oh, that's a great question. Yes, sir?
Do you have the technology to get out far enough, catch the asteroid early enough, use a gravity trap?
Oh, sure.
Or similar?
Yeah. Yep. The real trick would be, if it's a near-Earth asteroid, it's already passing near us all the time. And so what would an early detection be? It wouldn't be an asteroid that's way out on the swing when it's going to hit us. It's that we figured out we've got 3 swings left. And on the 3rd swing, it's going to hit us. So we just wait for the first flyby when it's not going to hit us. And then we wait for it to do all the work for us. And we park the asteroid park our spacecraft or whatever we're going to do with it on a flyby. And then now it's just hitching a ride, and hopefully it changes it enough such that on that later swing by the Earth, now it's just slightly altered. And it only takes, look at how fast we're traveling around the sun. If you just wait 1 second, you miss Earth. Or wait, no, not 1 second. 20,000 miles to Earth is so big. So if you wait like 5 seconds, you miss the Earth. So if you change, you can think of it that way too. We definitely have the technology. It would just be how accurately have we nailed how that object's moving. So we would turn all telescopes toward it, maybe need some new ones. And then, how accurately can we intercept and run it? So it would be all about precision. But yeah, we've got the tech. Oh yeah, it depends on the period. I mean, some of them are longer, but they're all near Earth, so they're near the same velocity. So they all tend to have sort of within one order of magnitude. You're talking years, not decades or centuries. Yeah.
And that's it.
Yeah. Yes.
So I think Mars is closer to the asteroid belt than Earth.
Yes.
Does that mean they get hit more than Earth? And two, if so, is the increase sufficient that they need to include that as a risk factor in all this talk of events in Mars?
Well, guess what? We don't have enough info, so we better go to Mars, huh? No, I'm being glib, but Mars has an atmosphere, so it's eroding too. It's less active, so we've got evidence of ancient meteors, impacts. But the statistics back up what we know about how often everything in the inner solar system tends to get hit by stuff. But as far as, what's the difference in Mars' strike? We just assume all the inner planets are the same. And of course, they're probably different, but asteroids get, as something falls, the fastest part of your orbit is when you're close to the inner swing. So think of it this way, if something's coming toward, if an asteroid, say, started Mercury, all the asteroids that are swinging around the sun are at their fastest, because they're all ellipses. They're at their fastest when they're inner solar system, and then they're slowest when they're outbound. And so everything's going to hit Mercury harder, faster than Earth, just based on its distance from the sun. So you'd expect it, even though Mars is closer to the asteroid belt, based on how far away it is from the sun, the near Mars asteroids that are flying around are probably going a little slower. So, I mean, it's a parallel question. Are there more of them, but they're going slower? But I'm trying to give you a window into the details that start to matter when you're trying to answer those questions. I'd still say there's enough shepherding that's gone on. The impact frequencies are probably the same overall, but they'll manifest differently. And also because Earth is pulling the asteroids in hard with its gravity field. Mars has 1/3 the gravity, so it's also not pulling on the asteroid and giving it an extra, so you see a difference there too. And maybe that means capture doesn't happen as much. I mean, that it's most likely that its two moons, Phobos and Deimos, are captured asteroids. So, yeah, we don't know. We don't know. The statistics are good enough where we say it's pretty much the same. But, we need more data. Yes, sir?
I'm curious if there are any work on hitting one asteroid with another one. I mean, that would be the perfect defense that this happens naturally, so why not doing it artificially?
Yeah, it's been a long time since that has really happened. You see movies like Star Wars and the asteroids are all flying around and hitting each other all the time. Space isn't like that. Space is too big. Space is like firing two shotgun blasts at each other at distances of, like 500 yards. What are the odds of the BBs hitting each other? There's so much space in space. Like when people say, there's too many satellites around the Earth, and they show these pictures, these ridiculous pictures of like a cloud of asteroids. They're not telling you that there are cubic miles between those things, at least. So the same problem with asteroids. Now that having been said, certainly, yeah, asteroid collisions have happened in the past. I think the greater value, there are too many, I would say, if we've manipulated one asteroid enough to move it into another one, I'd say why wouldn't we just use that technology to move the one we want to move? Or, but the problem with a collision is so many unknowns. And there's a big chance that you just make the problem worse. Whereas I think if we have one in our grasp, its biggest use is as a gravity tractor. We've got a lot of mass we didn't have to launch. And that's one of the big arguments for asteroid mining. It costs $10,000 a pound-ish to take anything from down here all the way out of Earth's gravity and put it up there. Anything. Junk, gold, platinum, diamonds, $10,000 a pound to start. So if you just get junk in space that started there, you could charge Earth people $10,000 a pound for it, because that's how much it would have cost to launch it. Give them a 50% discount and charge them $5,000 a pound, and all of a sudden your asteroid mining is really, you're making profit. So by the same argument, if you collect, a big chunk of rock you could never launch from Earth, one of its biggest values for this is its gravity field. Yeah. And also, there are other things too, radiation shielding and all sorts of stuff you can do with it before you can just mine it for pure elements. But yeah, I'd say if you had one in your hand, don't waste it by blowing it up. I'd say park it near one, drag that, and then you could use it again for a different one. You gravity tractor, anything. It could be your perpetual gravity tractor. Then you charge all world governments a maintenance fee, and then you're in business for the rest of your life. Yes. Any other questions? Thank you guys so much for coming. Oh, a couple more? Okay, no problem.
I've always wondered about this. Airplanes being driven by meteorites, astronauts.
But it could happen.
But if it were to happen, that one flight 800 that's never been solved, I just have a theory. You can tell me if it's
I don't know.
Take a bullet-sized meteorite going, 600,000 miles?
Yeah, it's
just happens
plenty
in
to
the atmosphere.
puncture a fuselage.
Puncture the fuselage. What would it do?
Well, if it punctured the fuselage, at that point, so here's one thing that all the movies and pretty much anyone who hasn't dealt with this stuff gets wrong. when an asteroid lands, so say someone says, an asteroid fell, or a meteorite, so it's a meteor when it's traveling, and it's a meteorite when it's on the ground. So if someone says, oh, I found a meteorite in my backyard, it just hit, and there's like you see it in the news, there's like a crater and like this thing. He says, oh, it smoldered, it caught the grass on fire, and it's like smoking and stuff. He's lying. The reason is, space is cold. Asteroids and meteoroids have been in space for a very long time, so they are cold. And I described at normal approach velocities how much thick air there is and how long it takes to cross the atmosphere. That means this whole rock is like negative 170 something degrees. And it travels through the air for what, 2 seconds? So yeah, you burned off that outer layer, but that's not enough time. I don't care how long. The air is just not that hot, or not that, depending on, the thermal conductivity isn't that good. So whatever hits the ground is going to be cold, space cold. And so that's one of those little forensic things you can use to sniff out the fibbers from the truth-sayers is whether or not it's reported as cold or hot. So,
I'm not saying that's
no, I know. But you reminded me. I thought it was a good point to make for the group that these things are cold. So when they come in, they're not automatically going to like explode when they hit because you're talking the small scale stuff. It'll have quite a bit of force. It'll tear a hole through the fuselage. Now, if it hit the wing and went through the fuel tank or something, yeah, you can cripple a plane. But you have to be really lightly stressed because they've got multiple engines just for any kind of engines. So you lose cabin pressure. The plane's not going to explode, but the little things are going to come down and people will get freaked out. And
people on the ground said they saw something. What if it was piercing and going through the fuel and coming down through it?
It's, hard to rule some. I guess the only question is like all the science is there any way to prove the idea wrong? If there's not, then we're done, and it's possible forever. But I think the real, if you want to chase it, think about how you prove it wrong. What would you need to find and look at? A fragment of, something. Because I agree with you. It's possible to take a plane down with a meteorite. It's not documented, of course, but no. Yes, I concur. Yes, I think you could take a plane out with a decent-sized meteoroid on the way down. Yeah. And certainly, I guess as plane flights go up, we might, with the 7 average Volkswagen Beetles per hour, maybe we'll see more of that stuff. But still, there's so many people across the world, and asteroid and meteorite hits. We haven't hit a person, so planes moving real fast. So the odds, get even if you get lost in stats land, you say, well, plane's moving so fast that the odds of hitting a stationary person are even better than a moving plane. So lots fewer, but it doesn't mean it can't happen. No, it's an interesting idea. I hadn't thought about that before. Yes, sir.
And I was going to ask, you showed the picture of all the orbits, trajectories, and everything. Is it possible to have like a celestial body or something too big that we can't detect?
Well, that's a good question. Probably not too big, but the question and answer would be you can have something too far away. And the reason is that if you go out past Mars, the sunlight intensity has dropped so much that you can't use solar panels anymore. At least not at our efficiency. That's why you need little nuclear generators to run things that go farther than that. So the sunlight gets so dim once you get out past Pluto that our sun it's 40 times farther away. They draw the solar system wrong. Pluto's 40 times farther away. Venus, Earth, and Mars are at like 0.7, 1, and 1.2 astronomical units. So they normalize the distance to Earth. So Venus is 80% of the way to Earth. Mars is 120% of the way. Pluto's 400% away. So this is really stretched out. So when you get way out there, and the intensity of sunlight, if you double the distance, you drop the intensity by a quarter, or to a quarter. So you double it, drop the intensity by 75%. Do it again, another 75%. So basically what I'm saying is, it's really dark. Really, really dark out there. And we're finding more and more things out there beyond Pluto, kind of in that realm. But there's enough gravity shenanigans going on out there with some of the long period comets and some of that a lot of scientists are seriously proposing something big out there, and big like Neptune big, like a big gas giant planet. But we can't see it because it would only, so there's not enough visible light to bounce off it and see in a telescope. And so the only thing we could see would be like infrared. But it's really cold back there too. So teasing a little infrared from like, guess what? This is where astronomy shows up. Nebula clouds are warm. Like in between, the lanes in between the stars. There's stuff out there, they call it interstellar medium. That's all about some temperature, and it's emitting infrared. So trying to see a really cold, even if it's big planet far away, where there's no light bouncing off of it, that's really difficult, and surprising. So yeah, if it's in the inner solar system, nah, we'd see it. But you can have something enormous out there, and it may swing in. It'd have to be on like eons time scales. But yeah, that's where you can prod on the unknown loitering out in the solar system. Yeah. Yes, sir.
So you can't see these things optically. Is there a technology that can still detect them, these dark objects, that are big enough to probably?
That's a $1 million question in astronomy right now. Is there are only so many ways to detect things. So you can look at the light they emit, any color, infrared, visible, or you could look for when they cross something. So if you get a star behind, and it moves in front, it casts a shadow, that's how you see it. And that's actually how we've seen most of the extrasolar planets. The same different version of the same problem. Planets around another star, they don't emit any light, they reflect it. And have you ever tried to look at an airplane right next to the sun in our own atmosphere? It's almost impossible to resolve it's too bright. So now imagine going tens of trillions of miles away and trying to find the fighter jet next to the sun thing at 9 trillion miles, and you got a big problem. So what they found is crosses, they call them transits, where the planets come in front of that star. And if they detect a pattern, they've actually gotten sophisticated enough where they can tell sizes and periods and distance, and then they'll look at the star's wobble as we move mutually through space. And they can calculate the tug that certain planets would need to be making, and they put all this stuff together and say, hey, we think there's a series of planets around these stars. So what technology exists today that's new, that's just been refined to maybe do a hunt like that? We're talking transits, but now you'd be looking at some deep solar system, you pick a spot in the sky, and you just watch all the stars and look for something that just blacks it out. And then that's where we could start to market, and this is where, full credit to the astronomers of old. Even in our own solar system, they had to wait a year for one measurement at a time. So you could start to tell a story over 10 years. Same day of the year and looking at the right spot if you had everything set up the right way. So you'd be drifting back into that territory. Like, hey, I got one spot here. Let's watch for another 5 years and see. But out at that distance, things are moving on like 10,000 year loops. So you have to start to make some interesting argument about, I would say it'd be some version of the transit analysis, but you have to like anchor your whole star field and like try and look for something that's blanking out spots along a trajectory. But if you're starting in the dark, you've got infinite trajectories, really. So it would be a needle in a haystack to start, but maybe you find something.
How far out in space can you find
No farther than we're finding Pluto stuff. Like you get out to the Kuiper Belt, that's what they call it, the icy stuff out there near the Oort cloud. That's it. We can't even see the edge of our own solar system. There's icy stuff back there, we know it, but we can't see it right now. So, yeah, it's a good question.
We made your plans for the eclipse?
Yes, of course. I am going to be in Teton Valley, Idaho. Right dead center. I want to look at the Tetons while I'm in the gaping holes in the sky. So if you guys are aware, there's a total solar eclipse crossing the mainland United States on August 21st. It's one of these once-in-a-lifetime things. I think the next one's in the 2050s. Of course, you could fly to Africa if you could do that, but this is going to start in the northwest United States and swing down through Idaho and Wyoming and cross down through Missouri and then you're on your way out. So there's a big stripe across the country. So if you guys are into that sort of thing, it really changes the perception. I hear people who see it, you realize that the sky, the air is luminescing kind of like a bulb when you see a hole punched in it and you can see the stars. So it's a way of awakening that awareness of, what's seeing the stars in the daytime. I just want to see that. But yes, great question. You guys have been so kind. Thanks for sticking around. Thank you very much.